Hello friends, welcome to engineering tutorial. So we'll continue our discussion related to alternating voltage and current. Previously we discussed the root mean square value of alternating current. So here we'll discuss the root mean square RMS value of alternating voltage. So the basic definition of alternating voltage and current we know. So alternating parameters or alternating quantities, they vary with respect to magnitude and direction. Magnitude changes continuously and direction it reverses periodically with respect to time after a certain fixed interval of time, which is called as the time period. So the application of an alternating voltage to a circuit results in the flow of an alternating current. The expressions of voltage and current, it is expressed in the form of sinusoidal mathematical expressions, which is Vt is equal to Vmax sin omega t. Vt is the instantaneous value, Vmax is the maximum value or the peak value or amplitude, omega is the angular frequency, and t is the time period. Here we have not taken into consideration any initial phase angle. This is the AC voltage waveform. Similarly, the current can also be expressed, which we discussed previously. So previously we discussed the RMS value of alternating current. So here also the process is similar, just in place of current our focus will be on voltage. Everything will be expressed in terms of voltage. So what is the objective of these calculations, the mean or average value and root mean square value, is to represent the alternating signal in terms of its equivalent DC representation. How the AC voltage signal, the varying signal, can be expressed in terms of a steady signal. That is the objective of mean value calculation and also RMS value calculation. So the RMS value expression, which we discussed previously by using the mid-ordinate method, is to divide a waveform, a portion of the waveform, a half cycle, into equal parts on the time axis, okay, and these parts, the equal parts, they are split into their middle part, which is called as the mid-ordinate value, okay, exactly the middle part, middle portion on the time axis, a dotted line is drawn, the red dotted lines, these are called as the mid-ordinate values. If it is a current signal, then we get the mid-ordinate current values. If it is a voltage signal, we get the mid-ordinate voltage values, okay. So this is the mid-ordinate. Then what we do here, we determine the mid-ordinate values I1, I2, I3 up to In, depending upon the number of mid-ordinates. Similarly, for voltage we will get the value V1, V2, V3 and Vn, and then we calculate the RMS values, which is given by this, okay, root over of I1 square plus I2 square plus I3 square plus In square by n. The mean of the mid-ordinate values, the root over of the mean of the mid-ordinate values. Similarly, Vrms is equal to V1 square plus V2 square plus V3 square plus Vn square by n. So here we have square root, here we have the average or mean of the squares. So that's why this value is called as root mean square value or RMS value. But the problem here, why this root mean square value was required, the necessity of calculating root mean square value, why mean value was not sufficient, the mean or average value was not sufficient, because you know, if we consider mean value or average value, it is only applicable for the half cycle, one half cycle, whether it is positive or negative. Preferably the positive half cycle is considered. But if we determine the mean or average value over the entire cycle, for the entire time period, the value is 0, because the positive half cycle and the negative half cycle, they are exactly equal in magnitude but opposite in direction. So that's why they cancel out each other, okay, and the net average value is 0. That's why it is not applicable for power calculations. So RMS value, the root mean square value, was used. Now the main requirement in mean or average value, as we also discussed in the previous video, is the charge, the total charge transferred in half of the time period. Here the main parameter of interest is the total heat energy produced. Here only half cycle is considered, so the time duration is t by 2 seconds. Here the entire full cycle is considered, so the full cycle of the alternating signal is considered, so the entire time period is considered, okay, t seconds, okay. So we know that the amount of heat produced because of the application of voltage V, the flow of current I in a circuit consisting of resistance R, can be expressed as H is equal to I square RT. This is the thing which we used for AC current, RMS value of AC current calculations. This expression we'll use for the alternating voltage. There is also another expression which is VIT. So this is derived from these two, okay. Any of the three is applicable, we can get the other value. So here we'll be using this one, okay, V square T by R, because we are determining the RMS value of the alternating voltage. So what is the definition of RMS value of alternating voltage? So the RMS, root mean square, or effective or virtual value, as there are different names of RMS value, of alternating voltage is that value of steady voltage or DC voltage, which is this, which when applied to a given resistance for a given period of time, which is the entire time period of the signal, it produces the same amount of heat as is produced by the alternating voltage. Sorry, this is it. Here it is alternating voltage, not current. This is alternating voltage. Alternating voltage when applied through the same resistance, applied to the same resistance for the same time, okay, this. So what it essentially means is that suppose this AC voltage is applied for the entire cycle for duration, time duration t is equal to capital T seconds. For the entire full duration, full cycle, it is applied to this circuit, okay. And also this equivalent RMS voltage is also applied for the same duration, that is T seconds. In both the cases, the amount of heat that will be produced, it will be the same. If we apply this alternating voltage for T seconds and this equivalent RMS voltage, which is the DC representation of this AC signal for the same duration, that is T seconds, the amount of heat that will be produced will be the same. Same amount of heat will be produced. Heat produced is equal. In this case, also in this case. Okay, that means here Vt square by R into T, that is the same as Vrms square by R into T. Okay, this expression we have used, that is Vt square by R into T is the same as Vrms square by R into T. What we are trying to say is that this DC voltage, which is called as the RMS voltage waveform, is the equivalent representation of this AC voltage waveform. Okay, so this is the equivalent of this, and this is the equivalent of this. Okay, this is the AC equivalent, this is the DC equivalent. That is the objective of mean and RMS value calculations, to give us equivalent DC representations of the AC signal. In mean or average value, we take charge transferred, the total charge transferred into consideration. In RMS value, we take the total heat produced into account. Okay, there it is charge, here it is heat. There half cycle is considered, one half cycle is considered. In RMS, we consider the entire full cycle. Okay, that is the difference. So this is the definition of RMS voltage. This is the equivalent DC representation of this AC voltage waveform. Okay, this is the steady representation or DC representation of this AC voltage waveform. Okay, so this RMS value is equal to Vmax by root 2, which is equal to 0.707 Vmax. In case of RMS value of current, we determined IRMS is equal to Imax by root 2, which is equal to 0.707 Imax. So the same thing, only voltage is replaced, current is replaced with voltage. Okay, this. So now we'll derive how we got this expression. Okay, so here we'll discuss the RMS value of AC voltage. So let us say we have a circuit consisting of a resistor R, we have an alternating voltage Vt applied to it, and that results in the flow of an alternating current. Okay, so here let's say the alternating voltage is expressed as Vmax minus Vmax, this is time, and this is Vt. Let's say the alternating voltage is expressed as Vt is equal to Vmax sine omega t. The full cycle, it has a time period capital T. So when this voltage is applied to this resistor, it results in the flow of a alternating current and a certain amount of heat is produced. So according to the definition of RMS value, if we try to represent this in its equivalent RMS form, the DC equivalent form, then that will be expressed as this. This is Vrms. So this is the equivalent representation of this AC voltage. So if we apply this alternating voltage for a duration of t seconds, the same amount of heat will be generated as is done by the application of this DC equivalent waveform, which is the RMS voltage waveform for t seconds. Okay, so here we'll try to mathematically derive the expression. So let's say the alternating voltage Vt be applied for a small duration dt, time duration dt. Then the small amount of heat dH produced will be equal to Vt square by R into dt, because we know heat produced is equal to V square by R into T, or we can also write it as I square RT or also VIT. Okay, so we have used this expression V square by R into T. Okay, so in dt time duration, amount of heat produced is equal to Vt square by R into dt. Okay, so total heat produced capital H is equal to integration of dH from 0 to H, which is equal to integration of this expression Vt square by R dt from 0 to T for the entire time period, for the full cycle. Okay, so now we'll replace Vt as Vmax sine omega t. So that is equal to 0 to T Vmax sine omega t whole square by R into dt, which is equal to, we will take Vmax square by R outside, Vmax square by R integration of 0 to T sine square omega t dt. This, because Vmax square by R is constant, this is the only function with respect to t. So now we can write sine square omega t dt as, right, Vmax square by R, and this as 1 minus cos 2 omega t by 2 dt. Okay, so this is we get from here, sine square theta is equal to 1 minus cos 2 theta by 2, this. Okay, so we substituted that sine square omega t is equal to 1 minus cos 2 omega t by 2. So this is equal to Vmax square by 2R to 0 to T 1 minus cos 2 omega t dt. So this is equal to, now we integrate Vmax square by 2R to integration of 0 to T dt minus integration of 0 to T cos 2 omega t dt. This is equal to Vmax square by 2R into t, this is integration of dt is t, limit t to 0, minus this is equal to 1 by 2 omega sine 2 omega t from limit t to 0, because 2 omega behaves as a constant here. This is only with respect to t. Okay. Now now we can write it as V max square by 2r into t minus 0 minus 1 by 2 omega, so sine 2 omega capital T minus sine 0. Now here there is an interesting thing. See, we know omega is equal to 2 pi by capital T, where T is the time period, capital T is the time period. So omega multiplied with capital T is equal to 2 pi. So here this omega t, that is equal to 2 pi. So 2 into 2 pi, that becomes, this becomes sine 4 pi. Okay, so sine 4 pi is equal to 0 and sine 0 is also equal to 0. So this entire thing, it becomes equal to 0. So we are only left with this much portion. So that is equal to V max square by 2r into T. This is the amount of heat that is produced by the AC voltage signal over the time duration capital T, for time period T. Now suppose we apply Vrms, the RMS value of the AC voltage signal over the same time period T. Then the amount of heat that will be generated, that will be equal to V RMS square by R into T, as per this formula. H is equal to V square by R into T. Here we just substituted V with Vrms and T with T. T is equal to the total time period. This is for the RMS equivalent DC representation. The RMS voltage representation, which we were discussing previously at the start. Here the very basic definition of RMS, of root mean square value of voltage, is this. Here from the start we are discussing that suppose this AC voltage is applied for the entire full cycle for time period T to this circuit, it will generate a certain amount of heat. That heat we got by integrating this entire expression. We got that heat value is equal to V square max by 2R into capital T. Now suppose its DC equivalent representation, which is the RMS representation, that is also applied for the same time duration T. Then as per this formula, the amount of heat that will be dissipated, that will be produced, that is equal to V RMS square by R into capital T. So as per the definition of RMS value, both the heats, the heat that will be produced, they should be equal by definition. They should be equal. So that means V RMS square by R into capital T is equal to V max square by 2R into T. So here also T gets cancelled and here R gets cancelled. So that implies V RMS square is equal to V max square by 2. That implies that implies Vrms is equal to Vmax by root 2, which is equal to 0.707 Vmax. Okay, this is the thing that we are trying to derive. The RMS value of the voltage, that is equal to Vmax by root 2, which is equal to 0.707 Vmax. The same result we obtained for current also. Irmx is equal to Imax by root 2 is equal to 0.707 Imax. But here we are using the voltage dependent expression, that is Vt square by R into T. In that case, we were focusing on the expression It square R into T. Okay, so the expression of heat energy, in the previous case it was current dependent, here it is voltage dependent expression. So essentially the base process, the main objective behind these two derivations, they are the same, but we are using different expressions in both cases. In the previous case it was current dependent expression, here it is voltage dependent expression. So we got the same result. Okay, Vrms is equal to Vmax by root 2, which is equal to 0.707 Vmax. Okay, this.